So I think I will stop the video on my part. So make sure you have enough bandwidth for the voice. So first of all, I hope everyone is doing well, right? And I really hope the pandemic can be totally controlled, and then we can be back to the normal lives, okay? And also, it's quite interesting, for the students who ask questions, they can get some awards, right? So this is very unique. Maybe people cannot wait for me to finish the talk so then they can ask questions. But anyway, this can be an interactive session, right? So if you have questions, please feel free to type into the chat window, and then the session chair can maybe stop me and ask the question, okay? All right, so let's start. Okay, so the workshop title is ROAD4NN. So then let's take a look of the road for AI, right? So why AI becomes so popular, okay? So there are multiple factors. The first one is, of course, big data, okay? So every day there's a large amount of data flood us, right? So Facebook, Google, and let's see, Google can support more than 100 languages, right? So then those just become raw material to train a machine translation model, right? So this could not be achieved previously, okay? And then for the computing side, right? So cloud computing is so dominating. So then machine learning becomes more affordable. So these days, as long as we have some GPUs and or as long as we have some credit from Amazon, from Google, right? And then we can leverage their computing power to train the model, right? It just becomes more affordable. And then the third parameter is, of course, deep neural networks, right? And we probably still remember Google started to recognize cats. Okay, so this is like 5-6 years ago, and the quality is reaching or exceeding human intelligence in many different domains, right? Not just cats. Okay, so by the way, this little cat is my own cat. Okay, pretty cute. And then we have the hardware advances, right? GPUs, right? So this is NVIDIA's CEO, right? And then FPGAs, GPUs, and right. So these accelerators can really help pushing the machine learning, pushing the AI algorithm development, really, pushing them forward rapidly. However, okay, there's always a but, okay. So we are facing many different challenges. The first challenge is a huge compute demand, okay. So here is the curve, it's plotting, right, so this is logarithmic, right? So it's exponential curve, okay. So then we know like 6 years ago, AlexNet was invented, and now we have this AlphaGo 0, etc. So what's the gap between 6 years ago and now? What's the computation demand gap? Can you guess? It's 300,000x. So basically the compute demand doubles every 3 months. Okay, so this is much more severe. You can think it's severe, right? Than Moore's law. Okay, so Moore's law is a good thing, right? And but this compute demand, this exponential increase is not good, right? So if that's the case, if we do not have a very good design, and then the computation becomes so power hungry, and then it's think about it, it's not even good for climate, right? Because just consuming so much electricity and contribute negatively towards climate change, right? Okay. So on the left side is for training, and on the right side, if we take a look, similar trend is happening. Okay, so for the inference, right? So this is where a lot of the classification, decision making is made, right? It can be made in the cloud, but now the trend is to really move to the edge, right? So I'll talk a little bit more about that trend, and then you can see both the total number of operations and the total number of parameters are increasing, right? So this trend is also very alarming. Number two, the challenge is kind of related, right? Because of the large amount of parameters we need for these high quality deep neural networks, and then it will require a huge amount of memory. And then let's take a look, right? So using one example, right? So this is a VGG16, right? So for many applications, we need to deal with high definition inputs. And then this is extremely difficult for edge devices, right? So let's take a look here. So starting from a convolutional layer 2, the number, right? So the size of feature map already reach 250 megabytes, right? So then how do we really deal with this large amount of intermediate data becomes a big challenge. So then as a result, right, so people are really trying to figure out, right, how do we really meet the real-time requirement, right? So here I mentioned, a lot of video process need real-time, frame per second, right? And then many compelling AI applications such as self-driving cars, UAVs, and require millisecond response, right? So because there's a safety kind of critical need there, okay? So people did some study. If we go into this real-time domain, then not many deep neural network can actually qualify, right? So only the lightweight deep neural networks can fit into this area. However, if it's not designed well, then their quality of results, so basically accuracy will suffer, right? So how do you really meet high accuracy and real-time constraint, hardware resource constraint and power constraint? That's the fundamental challenge. Okay, so what can be an effective solution? So most of us are familiar with the existing solutions, which is a top-down solution, where the data scientists will design the algorithms, right? They mainly focus on high quality, high accuracy, etc. So there are various type of competitions, right? Like ImageNet, that was a competition, right? And then they try to fit the AI algorithm onto the hardware, right? Including the edge AI. But this top-down effort actually has quite several drawbacks. So I will explain more pretty soon. And actually a new design method for edge AI is required. And in our proposed idea, it's called algorithm and hardware co-design. And actually many researchers, maybe many in the audience are working on this as well. Okay, so we just started early. Okay, that's all. Okay. Okay, so then what is a top-down DNN design and the deployment flow, right? So first of all, we have a team or several smart graduate students, right? So start to design the deep neural network because now the framework becomes so flexible, right? So TensorFlow, PyTorch, it's relatively easy to really get access, okay? And then after the algorithm is designed and we had different software related optimizations such as quantization, pruning, etc., trying to minimize the complexity of the software itself, and then try to map that to the hardware But because you know, software and hardware are two different animals. Sometimes they do not even talk to each other in the same language. Okay, so then there must be a gap between them. So then naturally there's iteration, and then the hope is, okay, I can still maintain my software quality, right? And then try to implement in the hardware and meet all the requirements, okay? So what are the drawbacks of this top-down DNN design and the deployment method? So then I kind of touched on this already, right? So software and hardware, they have different metrics, and many times these metrics are in conflict with each other, okay? So then it's difficult to select appropriate reference DNN at the beginning as well. Okay, so these days there are so many choices also. And should I take like a heavy duty DNN that's highly accurate, and then just prone it very aggressively and try to map to the hardware? Would it work? Or I just build a lightweight DNN from scratch? Or do I go from the middle, right? So since there's no guideline and the design space is huge, and then if people just try it in an ad hoc way, then you know the final solution is really becoming unpredictable. And then so here, so we can see this is the top down, right? So in a graph format, so people would try to design high quality software and then try to map it to the hardware. So each of them need multiple iterations. And then if it cannot converge, then you have these big global iterations, right? So in general, this can become very lengthy and then also become suboptimal, okay? So then, so naturally, people would think, okay, we cannot go through this kind of tedious, long iterative process. Can we design the software and the hardware simultaneously? You know, so it's not an easy task, but at least that's the right question to ask. Okay. So what is a simultaneous algorithm accelerator co-design? Okay, so move this away. Okay. All right. So conventional hardware. Here I introduce a NAS, right? So this is a neural architecture search, right? So this is automated neural architecture design, right? So that was mainly advocated by Google at the beginning, right? So they have a huge amount of computing power, right? So they can automatically search neural architecture. And then later on, people realize, okay, when we do the neural architecture search, I better consider hardware. So you become hardware awareness. However, here you can see the hardware itself is not co-searched. The hardware is fixed. Okay. So then for the simultaneous algorithm accelerator co-design, we can see the accelerator is also searched, and the accelerator can change, right? So then they are co-searched and co-designed simultaneously, co-optimized. And at the end, after this co-design, both the DNN and the accelerator are the outputs. Okay, so I just briefly talk about some of our DNN and accelerator co-design work. Okay, so these are the works we did since 2018. Actually, this first paper, as far as we know, published in 2018, first introduced the idea in a conceptual level. Okay, and then we start to implement this idea, and then our first kind of fruit, right, to materialize the idea is published in DAC 2019. Okay? And then we published some other works, but in this talk, due to the time limit, I'll mainly focus on the SkyNet, okay, and the EDD. Okay, So just one slide to introduce this idea we proposed in ICSICT 2018, right? So we propose a co-design engine, okay? And the objective of the proposed co-design is to automatically generate both DNN models and their corresponding implementations as pairs, okay? So it's no longer hardware, software, jump into each other and hope they agree with each other, right? So we just right at the beginning, make sure they are friends and then grow together, okay? And improve each other together, okay? So as a result, we can shorten the DNN development time by avoiding tedious iterations between DNN model and its accelerator designs. So, just by looking at this graph, you can see it's actually relatively simple, okay? So we have the hardware constraints. So here we use FPGA as a driver kind of platform, right? And then we have the different goals, and then we have an IP pool, okay? And then we will use these building blocks, right? So each IP is supporting one unique computation component, right? And the components are the building blocks for the deep neural network as well, okay? So then we can co-search, and then eventually we can produce different solutions, and each solution contains both the DNN and the accelerator. All right. So then 1 year later, so this co-design idea is materialized, okay? So we actually have a bidirectional idea, right? So you can see on the top is the DNN model, on the bottom is a hardware accelerator, okay? And then we have bottom up, which is architecture template guided DNN model search, okay? And then the top down, then we can evaluate the DNNs through architecture template mapping, okay? So both of these things are happening simultaneously. So then, so it's bidirectional. You can see after some iterations, right? So the DNN model and the hardware accelerator pair is improving after it's converged. Then we have both results at the end. Okay, so I'm not going to talk about the details, but then you can see the overall flow becomes more complicated than the one we proposed 1 year earlier, okay? So this is because high quality DNN design and its accelerator design are both challenging, okay? So then co-design significantly expands the design space. So it's difficult to converge and requires a novel search methodology. So here in a nutshell, we can see we have the auto DNN, so it's basically it's a NAS engine. It's embedded a NAS engine to search the DNN, okay? And then the good thing is we have auto heterosynthesis. So for each DNN, we call the heterosynthesis to generate the hardware. But of course, we do not call every time. Then that will be quite time consuming. We have a hardware model to guide it. But then for the final results, we can call. So the whole thing becomes automated. Then you can see the auto HLS will generate the hardware, and the auto DNN will generate design methodology. Actually, we produce this so-called SkyNet. So if you pay attention to DAC SDC, right? So this is a system design contest, okay? We actually, the SkyNet actually won a double championship because there are both FPGA and GPU categories, and the SkyNet became the best for both categories. Okay, so I'll introduce a little bit more details pretty soon. So, okay, I have about 25 minutes. So let me speed up a little bit, okay? So there are 3 stages for the SkyNet methodology, okay? So by the way, this method is also published in MLSys this year, okay? So what are the 3 stages? The first one is select basic building blocks, okay? Second one is explore DNN and accelerator architectures. based on templates, okay? And then the third one is some fine tuning, right? Add additional features and hardware deployment, okay? So you can see here we mark stage 1, right? So there are these different building blocks that we designed, okay? And we call them bundle, and you can see different bundles from bundle 1 to bundle N, and then we evaluate them. And then using this bundle, we build a deep neural network on the stage 2, and on the stage 3, we add additional features. So that's the overall flow. So what is this basic building block, so-called bundles? Okay, so bundle is a set of sequential DNN layers as building DNN, as basic DNN building block, right? So then you can see here, bundle is the building block for both the DNN and also the accelerator, right? So then when we design the bundle, we know, okay, this bundle can be, how to say, replicated, stacked, right? It can be expanded, right? And so then we can build the DNN, okay? But in the same time, the bundle is designed with hardware in mind. So then we know the bundle can be very efficiently implemented in the hardware. So then this bundle becomes a bridge between the software and hardware. So then instead of fighting between software and hardware, we have a kind of a mediator, right? So the mediator is good for both. And then as long as we pick the good quality bundles, then we cannot go wrong, right? So that's the design methodology. So here is one example, right? So this is like a building block, right? And then when we can use this building block to build a deep neural network, right? So here we just replicate the bundle, right? So this is like a ResNet type of construction. So we know ResNet can go very deep, but each layer is almost identical, okay? But of course you can expand on the different channels and all that. And then the bundle also has the hardware implementation. So then the co-design is, how to say, well constructed and also well constrained. So we do not need to jump everywhere and trying to search, okay? So here is the architecture design, right? So this is using FPGA as a template. So I don't need to talk about a lot of details here. So you know, what we try to emphasize is we can have this inter and intra-layer IP reuse, okay? Because the resource is very limited, okay? We cannot just instantiate IPs everywhere, right? So I have to instantiate some important IPs, and the IPs are shared, okay? So then, because the resource limited, the IP cannot be too big. So then typically you have to partition the input, and then each of this chunk will be run on the IP in different time. So it's a sharing IP, but in a pipelined way, and then the IP can be shared across different layers as well. Okay, so this is like we are designing a dedicated processor with 5 stages. Okay. All right, so then let's go through this step by step. Okay, so I kind of highlighted the features already. So let me introduce a little bit more detail. So then this is a stage 1. So we'll build the DNN from choosing the hardware or bundles, right? So that the bundle capture hardware features and accuracy potentials, okay? So what we do is we prepare DNN components, we enumerate bundles. So we actually have a search algorithm to search among different bundles, and we evaluate them, okay? And then we have this Pareto curve for the bundles, right? And then we pick those in the Pareto curve, okay? And then after we are done with the building blocks, so the next one is to explore the DNN architecture to meet the hardware-software metrics, right? So I also explained, so here we just replicate the bundles, right? But then we can change channel expansion, right, for these different layers within the bundle. And across the bundle, we can decide whether we want to insert a pooling, right? So these are the, like a hyperparameter we can tune, and they need to be searched actually, because this is a NAS, right? So NAS as an embedded function in our code design methodology, okay? So then how do we really solve this multi-objective optimization problem, right? So it considers both DNN accuracy and all that, and hardware throughput and, you know, power, right? So things like that. So then what we do is, you know, as I explained already, select the selected bundle, explore these hyperparameters using PSO. It's a particle swarm optimization. It's one type of evolutionary algorithm, okay? And then we evaluate the DNN candidates on top of this. Okay, so then let's see how this PSO works, okay? So we actually come up with a fitness score, right? So it include the DNN candidate accuracy and also candidate latency in hardware, okay? So then here you can see this TAR is the targeted latency, and this is the estimated latency for one candidate of the DNN, okay? So alpha is negative. So then you can see if the estimated latency is bigger than the target latency, then the fitness will drop. Okay. So then here the fitness function will just naturally consider both DNN accuracy and the hardware friendliness. Okay. And then the reason that we pick the PSO is that it can consider the grouping strategy, right? So here we actually have different groups. So within each group, we have different DNN candidates. So each DNN candidate will have a different kind of different parameters for the bundle stacking, for the channel expansion, etc. Okay. All right. So then what we do is we launch this PSO kind of search, right? So here we basically use this high dimension vector, right? So this, the number of stacks and right, channel expansion, etc. Right? So these become the feature vectors, and we use them to do this grouping-based search. Okay, and then PSO actually has both position and velocity. Okay, so then we consider the local best and group best, right? So the group best trying to consider a kind of global optimization. So we will not get stuck at the local minimum. So we hope we can get some grouping strategy that can pick out the high quality designs. Okay, so then here it's guided by both local and global, and then finally our goal is to pick the best candidate. All right. So then after that, we can, we pick the good DNs, and then on top of that, we can fit in some customized designs, right? So, so this is extremely helpful for this DAC SDC competition. And so we consider the small object detection, feature map reordering, etc. Also for hardware efficiency, we use ROAD 6 instead of ROAD. So which means any value greater than 6 will be just clipped at 6, right? So then we can use less hardware bits to represent the values, okay? And so here is the top design, right, for FPGA, right? So on the right side, I already talked about the hardware features. On the left side, so this is the embedded FPGA. So we have the embedded core that's doing some kind of pre-processing. And then we have the PL, all right, so that include all the IPs and on-chip buffer, and so efficient communication. So then we can overlap communication with computation. So let me quickly introduce this competition, right? DAC SDC competition. So it target both GPU and FPGA. Right? GPU is TX2, FPGA is Ultra 96. Okay, both are targeting embedded systems. So for the image, so if some of you actually join the competition, you are definitely familiar, right? So there are 95 categories of target objects. And then the evaluation need to consider both accuracy, throughput, and energy, right? So it's not just, okay, I have very high speed, but my accuracy is low, or I have very high accuracy and it runs very slow, right? So it has to be high accuracy and in the same time trying to meet the real-time constraint. Okay, so what we did is we analyzed the objects, contained in this data set, and we realized many of them are very small, right? So for example, 91% of all the objects are actually smaller than 9% of the input image. And 31% of all the objects are smaller than 1% of the input image, right? So then we have to really pay attention how to detect the small objects, right? So here are some videos. Then you can see, actually, I don't know whether you can see or not, in the middle, this is actually a person riding on the horse, okay? And then on the right side, we are not detecting this boat, but we are detecting this person behind it, right? So you can see it's actually quite challenging, okay? So here is the SkyNet architecture, right? Based on our bidirectional search, okay? So you can see indeed, this is bundle based, right? So they are identical. And then sometimes we insert max pooling, but then the channel numbers are different, right? And then with some fine tuning, we actually add some bypass. So then if you just keep going through all this, the object become too small. And then we can bypass, the object can be maintained, the size can be maintained. And the end, you have more feature map, and that can help for the regression anyway, okay? So we can target both FPGA and GPU, okay? So then here you can see this is overall design from the computation parallelization point of view. Okay, and then let's look at the results. This is evaluated by 50K images in the official test set. So then let's introduce our result. You can see we show both 2018 and 2019 results, right? So let's show the SkyNet GPU 2019 result. So then you can see we are actually 2.3x faster than the second place and third place. Actually our accuracy, right? So the IOU is the accuracy is also slightly better, okay? And so then of course, everyone is better than the 2018 results. Okay, so that made it fun, right? So the whole thing is improving, and so that becomes more competitive. So then let's take a look at the FPGA part. So FPGA part, we also got the first place, and then you can see the main reason is we are 10% more accurate compared to the second place and the third place. Okay, so then after that, we extend SkyNet to real-time tracking problems, right? So the tracking actually is different from detection. Okay, so here we use this called 10K, and cover different objects in the wild. Then you can see, right? So you can run into complicated scenarios. Speed are changing, size are changing, occlusion, and the angle, and all that. It's quite challenging. Okay. And what we did is we use SkyNet to replace ResNet 50 as the backbone, right? Because this state-of-the-art tracking algorithm actually use DNNs as the backbone to extract the features. And we evaluated 2 state-of-the-art trackers using SkyNet as the backbone. And then we can see, so the AO is an average overlap, right? So we can use that as the accuracy, right? So SR is the success rate when the IOU is either 0.5 or 0.75. Okay, so then overall we maintain the similar accuracy, but we are about 60% or 70% faster. Okay, great. So then maybe you will ask, is the code design problem solved? Okay, and you can probably guess the answer is no. Okay. So in SkyNet, DNN and its accelerators are searched coordinately, so that's good. However, you can see it's kind of coarse-grained, right? So we design some DNNs, you know, and then it's not very comprehensive, okay? So, and then we have this search algorithm, it's efficient, but still it's kind of greedy, right? As a result, we are exploring limited code design space. So the next question is there a more elegant way for code design space formation and search? Okay. So then our goal is to form a unified and holistic code design space, and then search the code design space systematically and thoroughly. Okay. So that's the goal. And so that's the next work I'm going to talk about. That's going to appear at the DAC 2020, right? So actually, I encourage all of you to attend DAC, right? It starts Monday, okay? So this work is called EDD. And so we probably all familiar with BDD, but this is EDD, Efficient Differentiable DNN Architecture and Implementation Code Search. Okay, so what is the key idea and what is differentiable? Okay, so let me try to explain. So we have these two design spaces or search space, right? So the upper one is a neural architecture search space, okay? And the bottom one is the implementation search space. So for the upper one and for NAS, there are different ways to search the DNN. So of course, there are these evolutionary ways, right? So invented by Google and others. And then later on, there's another type of search. It's called the differentiable DNN search. Okay, so I will explain what is differentiable, right? So differentiable means actually people can use gradient descent to search the algorithm. So it's more fine-grained and can be much faster. Okay, so but then our goal is to have this merged neural architecture and the implementation search space. So it's not just A, it's A and I, but need to be differentiable. Need to be differentiable. Okay, so then we can solve the AI co-search, A and I co-search using gradient descent. All right. So then let's take a look of existing work formulation and our proposed co-design differentiable formulation. Okay, so for the existing one, it has, you know, accuracy loss and the performance loss, right? But the performance loss for most of the NAS is considering a fixed implementation I0. Okay, so for SkyNet, you know, if you pay attention to that fitness function, it's similar to this formula. And but of course, we can also try to change the hardware implementation. So SkyNet is one step further compared to the existing kind of NAS search. But our goal is to have a more elegant, right, efficient search algorithm. And then you can see we actually have three parts, okay? So then the, you know, for the accuracy, it will consider both architecture and the implementation, right? Because implementation will definitely impact the accuracy, right? So we all know if we can, how to say, let's say we use FPGA as a hardware, and then we can use LUTs to implement the binarized DNN, right? So extreme kind of quantization. So then the accuracy can drop. Or let's say the original architecture is a floating point, and then you quantize it down to 8-bit, right? So sometimes the accuracy will drop too, right? So you can see indeed the implementation contribute to the accuracy as well. And then in the same time, we need to consider the performance loss. So because implementation impact the performance a lot, right? And then we need to consider this in the code search. And then in addition, we need to consider the resource, right? So we have to honor the resource constraint, okay? So then the similar thing between the previous NAS and our proposed code design is that on the A part, they are all differentiable. But the difference here is, as I mentioned, right, previously people understand only do a fixed implementation. We consider the implementation as a variable as well. And this can be co-searched. And then we honor the constraint. So the challenge is how to formulate I as differentiable with respect to L, right? So I think that's the new challenge we need to overcome, okay? So then let's look at this overall flow, right? So this is a differentiable design space. So this part we can be familiar, you know, if you have studied neural architecture search, differentiable architecture search, such as DARTS, right? Some paper like that, right? And then this part is brand new, right? So we'll have the implementation search as well. And then everything is nested together. So then we have a unified coherent code design space. So how does this work? Let's take a look at the differentiable neural architecture search. So what happened is, as I explained before, you still have this DNN, you have these blocks, right? This block is like the bundle, you know, introduced by me, right? And previously, and however, what happened is, you know, in this block, it has the inputs, outputs. These are the tensors, but you can have different operations, right? So let's say this operation is this bundle, right? So count one by one, depth wise, count k by k, etc. Okay, and then you can have another operation. It's like another bundle with different convolutional kind of computation, etc. So then here is really introducing some flexibility and alternative to operate on the input and produce the output. Okay, so then as long as these parameters are designed in such a way it's differentiable, then people can use a supernet, a so-called supernet, to produce this DNN. And then this DNN, you can see it's naturally embed many different type of DNN solutions, right? So let's say I have a bunch of block, and then during search, for this block, I pick the OPIM, right? And then for the block down here, maybe I pick another operation, right? So all these are searched, but because it's differentiable, right? So at the end, you just converge, and then you can extract the good subnet, which become the final DNN. So that's the fundamental idea. Okay. So then for here, what we did is we actually borrowed this idea invented by you know, FDNet, right? So last year, it's called Gumbo softmax. Right, so you can see, right, so to pick one particular operation, this is actually, it's not a continuous, right? So to be, you know, to be differentiable, we need to make it continuous, right? So Gumbo softmax has that property, right? So after we introduce a Gumbo distribution into the parameter, right? So then it's converted into continuous, right? So I don't have time to introduce the details, but that's the trick to drive this differentiable search on the architecture side. And then on the implementation side, we are facing similar challenges, but in a different way, right? So let's say this is a depth-wise convolutional, and then we understand, okay, quantization is important, okay? And then again, we have to pick one particular quantization and evaluate its impact, right? And then there are other hardware implementation parameters. So let's say we pick a qubit, right? This particular quantization. And then we have to consider others like parallelism, loop tiling, and all these are the hardware search parameters, right? So we also need to consider them, okay? So, but the idea is the same. We use Gumbo softmax to convert this non-continuous to continuous function, right? So they become differentiable. And then we can consider different stages, right? So level by level. So for the first stage, we basically evaluate the alternative bit widths, but then under each bit width, we can consider different implementation scenarios. So then you can see we have this performance function for a fixed quantization bit, right, to consider these different scenarios. Okay. So then, for example, here, this is for the FPGA, right, depending on whether it's convolution or depth of the convolution, right? So the latency can be evaluated. Similarly, resource can be evaluated, right, depending on the bit width, and right, so these are hardware specific, okay? And then after we design this function for bit width and for the hardware resources, hardware implementations, then we can come back to this operation level, right, stage. The operation level stage will need to consider all these different implementation scenarios, right? So then this is a stage 2. So I will not go through a lot of details. So this basically, we use this Gumbo distribution, consider all the quantization, so we can naturally embed the search space, okay? And then we continue to push, come back to the this block level performance and resource and accuracy, etc. And until we go back to the whole DNN. And then we do the search on top of that, okay? So then this is a differentiable code search, right? Consider both accuracy and the implementation. So that a little bit more detail, right? So I'm almost done. And so here, so consider the hardware part. If so, this is performance loss, right? So you're driving the loss function. If it's end-to-end latency, then the performance need to be summed up, right? For all the blocks, but if you're thinking about throughput, then it's determined by the largest latency of all the blocks. So we need a max function, which is not differentiable. Then we approximate it using a log sum exponential function, which is differentiable. So there are some other issues such as resource sharing and etc. So all this can be considered. Okay. So let's look at the experimental results. And using EDD, we actually produce the different neural networks targeting GPU or recursive FPGA, which means the IPs are shared. Okay, and pipeline FPGA, that means, okay, each layer has its dedicated IP on the FPGA, and then it's done in a pipeline way. Okay, so here are all the 3 different EDD nets searched, and then you can see they are quite different. The details are in the paper. Okay, so let's look at some results. So EDD net 1 is targeting GPU. Okay, so then we compared with some other hardware-aware NAS models, right, reported in the literature very recently, including this FBNet, okay, who used Gumbo softmax, right? So then you can see we actually have the best latency, right? So for example, we are 2x better than FBNet, okay? Then also compared to some other results, right? So next, we use the EDDNet tool, right? So this is targeting recursive FPGA, and we evaluated on top of the Chai DNN, okay? So, again, we have similar test error, right? Similar accuracy, right? And however, we are, again, our latency is the best. And we also compare to DNN Builder, right? So DNN Builder was a work done through a collaboration between us and IBM. And actually won the Best Paper Award from ICCAD 2018, right? So then we actually can also beat a DNN builder. All right, so in conclusion, we presented SkyNet and the hardware efficient DNN design method, right? It's mainly focusing on bidirectional DNN accelerator design. And SkyNet is effective, right, to capture the realistic hardware constraints. And then we propose this efficient differentiable DNN architecture, right, which is a fully simultaneous, elegant, and flexible, and we can target different hardware, okay? So then maybe you ask again, so is the co-design problem solved? And then you can probably guess the answer is still no. And this is actually an exciting research direction. You know, we can explore co-design for distributed AI, for heterogeneous and large-scale AI, right, and emerging AI technologies. So let me acknowledge the funding agencies and my collaborators, right? So it's mainly funded by C3SR and ADSC, SRC X Motors, Boeing, and Inspirit IoT. And you know, many smart and hardworking students and postdoc researchers made a lot of contributions. And also we collaborate with industrial researchers and with some other faculty members. I would like to really acknowledge Professor Tom Huang. And we all know he's considered as the founder of computer vision and who passed away, right? Very recently, so we will really remember him dearly, okay? And I also would like to acknowledge Dr. Chung Hao. Okay, I think she's in the audience. So she will join Georgia Tech as an assistant professor next year. Okay, and you know, she made a lot of contribution. And also my PhD student Xiaofan Zhang and Yu Hongli and postdoc researcher Yao Chen, all of them made a lot of contribution. All right, thank you for your attention. Sorry, it runs a little bit over. Yeah.
Yeah. Hi, Deming. Thanks. It's a very exciting keynote. In fact, we have many questions. I guess we cannot answer all the questions. So what we will do is, there are two attendees raising their hand. You know, we still have some time, you know, in the buffer. So I will let these people ask their questions. Meanwhile, I will send the list of questions to your postdoc, Tong. She is actually helping answering a lot of questions.
Oh,
so, you know,
okay, great.
Many of the questions can be, you know, probably answered in the chat box. Okay, so
that's right.
Nating, can you go first?
Yes, thank you, Professor. This was such an informative talk. I just have one question.
Yeah.
The basic bundle architecture, so it maps the IPs and the DNN layers. My question is, how do you choose which bundle to use, and how do you, like, is there an iterative way to choose the IPs and the layers, or do you have a fixed criteria that these are the IPs which we will be using, and we have a fixed set of IPs which we evaluate every time?
Right. Yeah. So that's a good question. So let's go back to this bundle idea, right? So yeah. So which one is the? So if we go back here, right? So what we did is we looked at some recent kind of innovations in the DNN design domain, right? So it's well known some bundles are just working better, right? So we pick those bundles as some fundamental building blocks, but then we do need to evaluate them. So what we do is we actually, for each bundle, we insert a front end and a back end, and then we use a subset of images to train them, okay? And then, you know, this bundle can be mapped to the hardware as well, so we know their latency as well. So then we will evaluate all these bundles, and then we pick the Pareto curve, right? So this you can tell bundle accuracy, bundle latency, and so we pick the Pareto curve on here, which means if a bundle is more accurate, then we are willing to pay a little bit more hardware, right? If it's not more accurate, but it consumes more hardware, then we will prune it away, right? So let's see this point compared to this point, the accuracy is not as high, and then in the same time, the latency is longer, right? So then, of course, this should be pruned away, right? So after we pick these bundles on the Pareto curve, then we use the bundle to build the DNN.
Okay, all right.
Yeah.
Okay,
Thank you.
Yeah, next, Chen.
Yeah, Professor Deming, yeah, very nice talk. I got one question regarding your last, results, like the comparison chart that you show. You showed your search is like 2x better than the rest the chart. Yeah, and how about the energy perspective? Yeah, that how about the energy perspective, like a power consumption perspective?
Oh, that's a good question. So, Tong, did we evaluate the power consumption?
Hello. Because we're using different GPUs, we didn't include power consumption in this comparison. But those GPUs, I think they have fairly similar power consumption. Say 20 watts. Yeah. So these are all NVIDIA high-end GPUs. So I would assume there are no such quite big differences.
Okay, got it. Yeah, thank you. Yeah, and then another question is that you use the accelerator like a FPGA based, the GPU based. Have you ever also considered that the option with like a reconfigurable ASICs or some like a ASIC circuits that perhaps that give us even better performance or even lower power, especially once you already zoom out to your optimization targets?
Yeah, right. So we considered ASIC, and we can learn from the FPGA experience, right? So FPGA is a customized hardware, right? So it's just very configurable. So for ASIC,
that's right.
It has most of the things are dedicated hardware, but maybe it has some reconfiguration, and all those hardware characteristics can be modeled within our EDD framework, right? So, however, in this particular paper, we didn't target it, but we do plan to target the ASIC designs in our future work.
Yes, they are type of ASIC called reconfigurable ASICs, which is really targeted, actually implemented in the silicon, like with metal layers, can be gluable, can be fusible, and which is targeted for reconfigurability. Yes.
Yeah, right. So we are aware of that, and so this is definitely an interesting direction. Yeah.
Okay, thanks. Actually, it's already the time. I'm sorry we don't have enough time for further questions.